this thing. So yeah, let me begin with a slightly more concrete version of the question. Okay, so
Okay.
suppose that f is a function from R to R. Okay, so f is a function from R to R, and it is continuous.
Yeah.
Now, let me ask you this. Okay, now if let's say f of x equals to f of x plus 4, okay, and also f of x equals to f of x plus 2, no, let's say 6, okay. What is the fundamental period of f? So fundamental period, you understand, the smallest period, okay.
Yes.
From this information, what can you say about the fundamental? So 4 is a period, 6 is a period, 8 is a period, 12 is a period. Good. But what's the smallest period from the question?
Okay.
Yeah.
From the question, it will be either 4 or it will be some number which is which divides 4.
Right. So try to see.
Okay. So it will be either 1 or it will be 2 or 4. It can be fractions also. Like
Yes, it can be those things. That's right. But can we say anything conclusive from what is given?
no, nothing.
No. So see, there is something which we can say.
Okay.
Okay? Just from what is given.
Yeah, but I just want to say one thing, like 1 second. 1, 0, 4, okay. 1, 0, 4, 6, 7, 8. Like this it is these properties also satisfied by constant functions also. So
No,
but constant functions, yeah.
no. See,
So
constant functions satisfy this. That is okay. But
yeah,
what will necessarily imply from here? So what you are saying is all possibilities. Okay. I mean,
yeah,
constant functions satisfy this, that satisfies this. If period is 1, that satisfies this. But from here, what can you conclude? You understand, right? Zero function satisfies this,
from
right? Just from here, what can you
yeah,
conclude?
yeah.
Means what will necessarily follow from here? Okay.
Okay, okay. X plus mm, that it should have a period. I mean, period can be 2.
You see, so that's something new you have said, right? But
Yeah,
what you have said will necessarily follow, and you can just show that by
yeah,
manipulation. I don't need to check, right?
mm,
So you can show that.
yeah,
Now this is something wonderful, right? Now you see, if this is good, because so basically what I'm trying to say is that this implies that f of x equals to f of x plus 2.
mm,
And how do you show this? I'm sure you can show it, right? Yeah, you can do it. So
yeah,
I'm not going into the proof. This is easy. So you see, if 2 periods are given, then basically their GCD is also a period. Okay. So if
yeah.
f of x equals to f of x, let me just remove it here and say, and I'll quickly move to the actual question because this is not the actual question, A and B. Then you can say that the D is that this is true, where D is equal to GCD of A and B.
Mm,
Right? Is it right? Can you prove
mm,
this?
yeah, yeah.
Okay, because GCD is a linear combination of the two numbers.
Mm,
You have to
mm,
use that, right? That the
yeah,
GCD D can be written as AX plus BY.
yeah,
Okay. All right. Now this can be said in language of group theory also, that the set of periods form a group, and so it has a cyclic group, and so generated by the period, and so on. But that's not necessary, so we are not going there. Basically, this is the
okay.
This is the basic thing. Now, actually, more things are true for rational periods and so on, but let me not go there. And let's come to your question. Now, suppose so basically the point is that there is an interaction in the periods is what I'm trying to show you. If two periods are given, then they interact and they produce some smaller period sometimes. Okay, at least in the integer
Yeah.
cases they do. Now, if I go to the question that you have, is like 1 is a period. Your question is somewhat like this, right? Right? Two irrational periods which are incommensurate. Like this is a standard example of that, right? So now we want to use, so far we have not used the continuity, right? We want to use the continuity and say. So again, from what you have proved, so from this linear combination of periods wala concept, we have, you can show, I'm sure you can show that this is true. Fine. F of x equal to f of x plus 1 equal to f of x plus 2 dot dot equals f of x plus m, right? So any linear combination of periods will work. M and n can be negative also. So basically, right? So basically, it is given to you that f is constant on this. So basically, f of 0 is equal to f of m plus root n, right? And this is true for all m and n in integers. It's a huge set on it, which it becomes equal. This is true for any period, right? If it was any 2 and 3 also, it will be true. So now we want to say that f is actually a constant function. Okay. So you see, so f is defined on this set and it is constant on this set, and we want to say that it's a constant function on all of the real numbers, right? So I mean, how do you usually show it? Now come to the definition of continuity. If this is x1, x2, dot, 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 it converges to x, okay? And let's say that if I tell you that these are all equal to anything, that doesn't matter, let's say equal to 1. Okay? It's given. So then can you tell me what is fx?
It will be like as x1 0 if
Okay.
0.
Okay, why 0?
But this portion is not clear. I mean, can you repeat
Right.
this part again?
Yes. So this is, so forget the upper part, just this part. F is a continuous function, okay? And there is a number x, let's say x naught. No, x naught is a bad notation, x only. Suppose it's x1, x2, the sequence converges to x, okay?
X, yeah.
And f of x1, f of x2, they are all equal to 1. Fine.
X1, X2 all converges to X, and okay.
And f of
Okay,
x1
but
equals
how
to,
can you assume this?
how
Like
can you?
you are saying that X1, X2 all are converging to X, but how can you say like 1 is equal to f of, I mean f of X1 is equal to f of X2 like
Yes.
this
No,
in
no,
this way?
yeah. So I am also saying this is given.
Okay.
If it is given in
Acha.
the question,
Then we can say it like then in that case we can say that fx is equal to 1.
absolutely. That's a very simple, right? Okay. So, right. So what I'm trying to say is that if you know the value of the function on x then you can determine it on x by taking the limit.
Yeah.
That's why
Yes,
that's
yes.
the meaning of continuity. Okay. And so
Yeah.
now if you want to show that f is constant, so we want to show that the goal is to show that f of x is equal to f of 0 for all x, right? We want to show that f is a constant function, okay? So,
You're not audible actually. I just don't know what is happening.
oh, am I audible now?
Now it's fine. Now it's fine. I didn't. I mean, मुझे इतना तक सुनाई दिया कि 1 = f(x)(1) मतलब f(x) इतना तक तो सुनाई दिया. उसके बाद कुछ
Yes,
सुन नहीं
yes, yes,
पाए.
yeah. So what I have just given an example of here, this is an example of a situation in which we are determining the value of the function at x by knowing its value on the sequence, right?
Yeah. Yeah.
Yeah. So
Hmm.
now we want to show that fx is constant for every x, right?
Yeah.
And so how
Hmm.
we will do it? We know that fx is constant on this set,
Hmm.
right? So we will show that given any number x, there is a sequence like this coming from this set that
Hmm.
converges to x.
Okay.
Okay. Now don't take it as something difficult, right? This is the
Hmm.
natural way to show, right? We want to show that these values converge to x. It may look like a
Hmm.
complicated thing, but it is not. Okay, will reform it and we'll show. Okay.
Hmm.
So this is fine. This is what we want to show. You agree? If you can show this,
But how can you get the intuition like ये पे ऐसा ही एक sequence मिलेगा जो कि उस number
nahi. So because see, yeah, because what the problem has told me
hmm.
algebraically, what is the algebra of the problem? The algebra of the problem is that f of x equal to f of x plus 1 equal to f of x plus root 2. This is just the algebra, right? There's no continuity involved here, right? Just function
हाँ.
and set theory. So set theory has told me this and set theory has told me this. Like some algebra and set theory करके हम लोग को यहाँ तक मिल रहा है. ठीक है?
Hmm.
अब अगर हमको
Hmm.
इसके आगे जाना है, if I have to go forward and show values at other points which the algebra does not
Yeah.
capture, then how will I go to
Hmm.
those other points? By taking limits,
Hmm. Hmm.
right? I mean, there is no other way, right?
Yeah.
From rationals to
Hmm.
irrationals to go, you have to take limits of rationals. Naturally
Limits.
speaking, there is no
Yeah.
other way. And taking
Mm-hmm.
limits is, so that's why I'm taking limits from which set? The set that is given to me, m plus n root 2, because I don't know the function outside this set.
Yeah.
Function में कुछ भी नहीं दिया हुआ है ना. Function is not given,
Hmm.
just it's given that f of 0 is f of m plus n root 2. From algebra you cannot get anything more
Hmm.
in the question.
Say.
So
Yeah.
given any other point, it has to come from a sequence like this. There is
Hmm.
no other way. I mean, obviously I know it from before also that this is dense, and I can see it from some other ways also, but that's aside. I'm trying to tell you in this way. Okay. Okay, so yeah, I mean, one can see this in many ways. That's a different thing. Okay, and Diophantine approximation or group theory, there are many ways to see this kind of things, but this is one way. Okay, now let us come to proof. So what we are basically saying is that this set is dense in R. Do you know the
Yeah.
definition of dense?
Hmm.
Okay, all right, and it's good enough, right? So basically, given
AC is
any
said to be dense in R if S dash is equal to R.
yes, and that basically means that any point is a limit point. Okay, given any point,
Hmm.
you can call it accumulation point or whatever. Given any point,
Hmm.
there is a sequence from the set converging to that point. Okay,
Yeah.
now we will again bring in algebra and simplify the question. So it's like algebra one step, analysis one step, and then algebra one step, and they together to give the proof. Okay, obviously
Okay.
I'm just presenting it like that. Okay, it doesn't have to be like that. When if you do it in a different sort of it's all is good. I'm just saying it like that. Okay, okay, but don't, if I'm saying more, it doesn't mean it's difficult. Okay, I'm just saying more because I understand it like this. Okay, don't
Okay.
think, yeah, don't think that it's difficult. I'm just saying it in this elaborate way. Okay, so now we want to just show that, so the problem has just reduced to showing that m plus n root 2, this set
Hmm.
is dense in R. Okay, what does it mean in the sense of a picture? To draw a picture,
Hmm.
it means that, well, given any point and any neighborhood, you can find something from this set which falls in this neighborhood. It is as simple as that. There is no sequence needed,
Yeah.
because you
Hmm.
can make the interval smaller, get another blah blah blah. This point is actually
Yeah.
also not needed. Given any
Hmm.
interval, you can show that it's there, then it's good enough, right?
Hmm.
Now you see, I have marked the point 0. You look at this set m plus n root 2. It's a very interesting kind of set. It's a group under addition. But to put it very simply, what it is that, says, think, if suppose that some beta is in this set, then you know that 2 times beta is also in this set.
Yeah.
Right? If something is there, then its translation by an integer is also there, right? If something is there, then 2 times. I'm not saying if something is there, then half of it is there. I'm not saying that. Okay, I'm just saying that if something is there, then integer multiple, addition, subtraction, those things are there. You can see that, right? Because if you add 2 things in that set, it is in that set, multiply by. So this means that this set is that's what it's called, a group. But if that is not required, that knowledge is not required. If you know it, then you can just think in that terms also.
I understood that why you said that it is a group. I understood it,
Right.
but
Yeah.
yeah.
Now
But
we will
what's the relation?
yeah, what's the use
मतलब
of
उसका
this? Yes, yeah. So basically,
हाँ,
just knowing the word group here is not useful. What is needed to be understood is that this set is a very interesting kind of set. It can be moved around.
okay.
And it's like if you are at a point beta, which is in this set, then you can move to 2 beta, then also you are in this set. Okay. How I will
Okay.
use this is, I want to show that given any random neighborhood, there's something from this set which is in that neighborhood. But I will use this moving property, okay, to just show this at the origin.
Okay.
Okay, that's how we exploit the moving property, that you can translate
Okay.
it. So now you see, if I
Okay.
can prove this at the origin, then I can prove it anywhere because of the moving property. Okay, but we will show the details later, but that's what the group structure allows you to do, intuitively at least.
Okay.
Intuitively, obviously, later on you will have to.
ये why you said like this कि origin में अगर वो हमें मिल जाएंगे तो बाकी points में भी मिल जाएगी.
Yeah, because so that's because of the moving nature of the thing, right? Suppose you find some beta here, very small
Yeah.
beta, right? Then can't you take 2 beta, 3 beta, 4 beta, 5 beta, 7 beta, some 1
हाँ.
million beta, and
Yeah.
come here? Right? And you
Okay.
won't
Okay.
jump
Okay.
outside. It's not that you 1 million
Yeah.
will be here and 1 plus 1. That will not happen because it's a small number. It will take small jumps.
Yeah.
Okay, so and there I'm exploiting the algebra.
Okay.
Right? It's a beautiful combination of the things. Okay,
Yeah.
so and obviously this is a special case of what is called a non-discrete algebraic subgroup of Euclidean space. So on things like that, okay, this is a, so because this philosophy is used that whatever happens at the origin, you can move that around and that will be true everywhere. See, that's the nature of addition, right? Addition is sort of the same everywhere. The multiplication is what changes,
Yeah.
right? Multiplying 2 times 3 is sort of has a different, 2 with 3 has a different effect as multiplying with 9 with 3. But adding 2 with 2 and 3 is the same effect as adding 9 plus 3. Right? The addition is sort of a uniform, yeah, it's sort of no, but the multiplication is a little bit of a thing. Okay, so that's what we are exploiting. These are very subtle and interesting points. So now I just want to show that it is dense near the origin. Okay, so well, this can be done in many ways. So this is in fact Kaczor. This is a problem in Kaczor. So if you have done Kaczor, have you done the sequences book a little bit?
Yeah. Not little bit. I did a lot, but it was many days ago, like 2-3 months ago.
Oh, okay, no problem. That's so. Maybe I will show you. This problem is there and that. We can do it here, but I'm just showing you that it is in there. So this is the sequence book, and here it will be there. See, and in fact they will have many more questions. This is a huge book. Means many more questions like this. Hmm. Just a minute. Basically, these questions are basically translations of that question. Yeah, this question, see, 1.1.15. This is straight away that what we are trying to prove.
Yeah.
It's
Yeah.
dense in R. Okay. And basically this earlier question which they have given here is also basically that question. So yeah, maybe let's try to explain why this is the same. This is also same as denseness, because you can, well, it's a little bit more, but it's at least that much, at least that. So what it is saying is this Pn is less than 1 by n, right? Okay, so I mean, isn't this saying that it is dense near 0? Because what is it saying? It is saying that you pick the point 0, you take the neighborhood 1 by n, right? And then an alpha is your irrational number, right? Then you can take m equal to this, and well, let's not say n or whatever, right? Some p, right? Some the other number n equal to this, and this will happen. That's what we are trying to also prove, right? All these are similar. They're not same question. This is more subtle, but at least it implies that our question,
Yeah.
right, that it is dense near. So alpha ke saath you take n times that, and you take minus m times this, and that number is very, very small. And then the shifting argument, so it is dense everywhere. So this question and this question are quite similar. Here there is a little bit more because they are no, it's not little bit more. The next question is a little bit more. Okay, but anyways, let's not get into all that. Yeah, so basically this is already done. Okay, but still let me give you an argument which may be different from what is there in the book. Okay, so you can see the book for the standard argument, but I'll give you a slightly more different argument. Okay, I will not prove that it is dense near 0. I will prove something else.
Okay.
So just for a different flavor. Okay, so you take 0, 1, 0, 1, and here what you do is you take this thing root 2, 2 root 2, 3 root 2, and so on, and you take their fractional parts. Okay. Okay. Now you agree that all these are there in this set because you can take away the integer part. You are allowed to subtract. All these are there. And because root 2 is an irrational, this is actually an infinite set. Because n times root 2 will never become an integer.
Yeah.
So this will never become 0. It will keep giving you different things. You can check that. So it's an infinite set. Okay. So, and all these are in between 0, 1. So now you're looking at an infinite set in 0, 1.
Yeah.
0, 1 is compact. Right? So if you have an infinite set or you have infinite sequence, it's sort of a sequence, right? It's a sequence. A sequence will have a convergent subsequence. Or just don't even forget compactness, right? A bounded sequence has a convergent subsequence. So you can use that idea. So what does it mean that it has a convergent subsequence?
It will
means
converge. It will converge to a point which is there in 0, 1 closed interval.
yes, in it only, right? So basically, this sequence will not converge, but a subsequence will converge.
Subsequence will converge.
Absolutely.
Yeah,
So you will have a point where this sequence will converge, right? So basically, around this, so it's sort of like this point is sort of well. So there is a slight hole in the argument. You will so 1 minute. Yeah, no, it's correct. Yeah, so it will converge here, right? Which means that no matter what epsilon you want, you make a neighborhood, there is something from this set which is in this, right? And in fact, you can find 2 of them which are in this.
How can you
Why
find
not?
2 of them?
I just make a smaller interval, right? Still, if there will be all of them will be in it, the sequence converges. From here,
From an epsilon from epsilon for a particular epsilon, we will get an m belonging to the set of natural numbers such that for all n greater or equal to m,
so you'll get infinitely, right? So at least 2 of them you will get, right? In fact, you get a co-infinite, but yeah. So now those 2 that you get, they will be very, very close. They will be less than epsilon close, and then that difference will also be in the set.
Yeah.
And that right, so that very, very small number will be in the set. And then you see, so you can do it in many ways. Now in the book, maybe they do by pigeonhole principle. Okay, they will
ये
divide.
कैसे किया मुझे वही समझ नहीं है, पिजन और प्रिंसिपल मुझे पता तो है, बट कैसे किया वो
That
मुझे
you have to
समझ
see the
नहीं
proof.
आया।
Read the proof, try
मैंने
to see.
देखी है,
Oh,
मैंने
see it again, and see.
ओके
Yeah, try. That's I've already given one argument. See that. These things are
ओके
these things are very, very interesting. So they go into interesting things. So then we are done. Problem is done, right?
ओके,
So we
आई
showed the
अंडरस्टैंड।
denseness. Yeah. A lot of interesting
या
things. Yeah. And then for your, I mean, that your question, it is, yeah. So let's actually see, because your question is not exactly this, right? It is, let's say, alpha 1 and this is alpha 2, and these are incommensurable. So the ratio is irrational, right?
या
Yeah. So let's see. So we'll basically have to show that that number is dense, right? So I mean, this set, we want to just show that this set is dense, right? But well, and this is dense. What can you prove? So we have shown something like this: m plus n alpha is dense, where alpha is irrational, and here the
या
ratio is irrational. Yeah. So well, if this is dense, is the same thing as this by alpha 1 is dense.
कैन यू रिपीट, आई मीन या
Yes.
हम तो ऐसे कर सकते हैं ना कि
Yes.
अल्फा 2 बाई अल्फा 1 को अल्फा ले लिया मैं हमने, यू नो।
Right. Yeah.
तो वैसे वो करने से तो हम जो प्रूफ किया तो वो सेम हो जाएगी।
Yes. Yeah. But for that, you have to first divide by alpha 1, right?
या
Yeah, and you can divide. That's true, because if a set is dense, then you divide every element of the set by alpha 1, it will still be dense, right? That that should be not difficult to prove, right?
या
Yeah, I mean, if you can imagine, if a set is dense and you divide every element of the set by some fixed number, why will that not be dense? That will also be dense, right?
या
Because
या
if you want to converge to x and you're using some sequence, then use for x by alpha, use the sequence that you use while converging to alpha 1x. Sort of, you can, yeah, or you can just say that it's a homeomorph. It's a homeomorphism, like a continuous bijection dividing by alpha 1. Real to real, x going to
या
x by alpha 1 doesn't change anything. So yeah.
या
So you can use many different things and say that's yeah. So that's it. Then your problem is also done. And there are many interesting dense subsets. Yeah, and that's the good thing about R, that R is uncountable, but there are many interesting countable dense sets. These are countable, right?
या
That's the beautiful thing about R, that this is a countable set and it is dense in R. Q is countable and it is dense in R. So many countable sets are dense in
या आई अंडरस्टैंड।
R. Right. So then, do you have any other question?
Yeah, I have like I 1.2.32. My concept is not clear, and 1.3.7.
So in the differentiation book.
Yeah.
Yeah. So what's the next question?
2.32.
1.2.32. Okay. Yeah. So let's try this. Yeah.
Okay.
Yeah. So again, you see the meeting, only 4 minutes are left. So I'll just end the meeting and then you join again. Okay. Otherwise,
Okay.
while explaining, it will end.
Yeah.
Yeah.
Okay.
Yeah. So just ending it.